Doing some Haskell learning today. Let me make sure this stream's working. I'll move you over here. Yep, should be working. All right, so I'm using a book called Learning Haskell by First Principles, and I've made a couple of videos. It's in my YouTube playlist, so you can look at that. But we're still on chapter 1. We're going very slowly. We're going to appreciate learning Haskell here. And we're just going to be doing some exercises. I can't actually show the book because it's copywritten. However, I can do the exercises with you, and maybe we'll just go over things. Talking to people have, some people tell me that it's like they didn't get what was going on in previous videos, or it's too complicated. And for others, I'm sure it's like, you know this way better than me. So it's a funny thing. I'm going to try to go a little slower and a little bit more simple. But yeah, go look at the other videos under the Haskell playlist, or get this book and read it through yourself. And then maybe the problems will make more sense at that point. So where am I? I'm on chapter 1, 1.7 right now, and it's basically talking about beta normal form. Beta normal form. I think I'm dyslexic. So that means like, is it fully reduced? Is it fully evaluated? When you have a lambda expression like the identity function, there's nothing more you can do. But obviously, if you give it like a parameter, an argument, like 3, then you can reduce this further and it turns to 3, because remember, this is the overall lambda expression. Here's one lambda expression in here, and here's the argument to it. So we're going to apply this function to this argument 3. When we look at this function here, the function has a head, which is on the left side of the dot, and the body's on the right side of the dot. The head is basically the argument coming into the function, and the body is the result, what happens afterwards. Hey there, Ice. And so like you substitute 3 into the head and you evaluate it. So if we do, this is a super simple expression because it's the identity expression, but we do x is equal to 3. And then obviously we look in the body and we substitute all the x's we see with 3, and we just have 3. And so now we're in beta normal form. But the expression itself is already in like this, is also in beta normal form. That's what the book's trying to say. You can't go any further unless it has arguments that you can apply to it. All right, the other thing that it talks about is in 1.8, it talks about combinators. I think that's how you say it. Oh shit, I am dyslexic. Or my brain just goes faster than what I can write. Combinators. And that just means that when you have an expression, we'll stick to our handy identity function here, that everything in the body here exists in the head, right? So if there's multiple terms here, that all of them are in the head. If they aren't in the head, here's an example of something that's not in the head. You have a y in here that's not in the head. So even if we give it a parameter to argument so that we can try to put it in beta normal form, the y can never go away. So x is going to become 3, and then the answer is 3y. And yeah, so that's not a combinator. And a combinator is basically it only combines the arguments that it has. So you know that it's always going to combine stuff. So they give a couple of examples, the identity function. They gave a really simple one of, I won't use the exact same one, but like here you have like an obvious free variable b that's not in the head. So we know that no matter what, we're going to end up with b as the answer. All right, so hopefully that made sense. We're going to do some exercises on this. So are you making YouTube video? Yeah. Yeah, the book itself is called Haskell Programming by First Principles. It's the book that I think is most recommended if you're having a hard time learning Haskell. It goes slow, gives you lots of exercises, and tries to teach it well. So I can't show the book because um it's a current book, not like my Atari books that's like no one cares about them, right? They're like however old. Um these are current books, so I'm not able to show it. All right, so 1.9 talks about divergence. Good book, Divergent. I think I liked it more than Hunger Games, just because like it spoke, like being neurodivergent myself, being different like in that way spoke to me, and sort of like her discovery that she's different. I don't feel like I have a superpower or anything, but yeah, decent book. The movies, I think I saw one. I don't know if they made them all, but it was pretty bad. All right, divergent means that like as you try to reduce it into beta normal form, it doesn't actually reduce. So they have it's called omega. I don't know why it's called omega. It seems like a lot of these things have a name for them, but this is omega. X in the head, and we have 3 x's. No, 2 x's, sorry. We only need 2 to diverge. And then we pass it a parameter. That's another function, right? So if we try to beta reduce, what we end up doing here is we're going to try to take this argument. We're going to apply the lambda expression to the argument. So it's basically x is equal to, and this function here, right? And now we're going to replace what's in the body wherever we see x, we're going to put this in. So you can kind of trivially see that this first x is going to turn into this, which is lambda x dot xx. And now we have a second x, which turns into the same thing. So we didn't end up, if we compare these two, well, they're the same thing, right? But also, we didn't get any closer to a reduced form. In this case, we're not getting like really further away either, but you can imagine that if it had 3 x's, that you'd get even further away, right? All right, so that's what the extra stuff we learned that wasn't in my previous videos, and now we have some examples to work on. So let's do that. Oh, I got such a dirty pad here. It looks way worse on the camera, trust me. Okay. So, the first question, this is 1.11 uh combinators. I did it again. Combinators. So the question is it a combinator or not? And remember, a combinator is when um everything in the body, all the variables in the body are in the head. So here we go. X, whoops. My X and my lambda look very similar. X dot X X X. Is that a combinator? Yes, because all of these, they're all X's, right? If you take the unique set, it's basically just X, and X is in the head, so we're in good shape. Second question. So the answer is yes. Check mark. I really should get water, huh? Oh, you asked if this is going to be, yeah, I'm hoping that it'll be a YouTube video. Maybe I'll get my act together enough to edit it so it's a more useful YouTube video. xy dot zx. Here we go. So we're going to ask ourselves, are all the variables in the body in the head? Z is not in the head, so it is a free variable, which means this whole thing is not a combinator. So we say no. Bad. I'm just thinking here. So the idea must be that, like, if everything in the body is in the head, then you're just basically rearranging stuff or simplifying stuff, right? So combining may be a weird word because combining kind of sounds like you're making more. But like, here, just like, hear me out for a sec. So if I did like x, y, y, x, right? I'm sort of combining things, or I can do this, right? So now you can see if I give it like 1, 3, right? This is going to turn into 3, 1, 1. So I'm like combining the input, this is my input, into something. But it could also be simplifying stuff, right? And in this case, if I give it like something like this, all it cares about is this first input. So even though it had like multiple parameters coming in, it actually is going to, the beta normal form is going to be 1. Just drops these. So combining is kind of an interesting way to call it, but I guess it just means that it's taking your parameters and it's going to return something that is only your parameters. You get it? Like only these things will show up in your output. It won't be Y, Z, or whatever. It's only going to be the stuff that is in your parameters, arguments. So that kind of makes sense, I guess. It's combining your parameters in a way somehow, rearranging them, whatever, but it's only your inputs. I'm just trying to make a mental model of why it's called combinators. All right, let's go back to the example number 3. Lambda xyz, and the body is x, y, z, x. Let's use our handy dandy sharpener. It's going to turn into Haskell ASMR. The combo you never knew you needed. Dude, I crack myself up more than I crack up you guys. All right, where were we? X, Y, Z, X. Right. So the question now is, are all of these in the head? Yes for the X, yes for the Y, yes for the Z, yes for the X. So the answer is true. I like how I say yes, no, and then it turns to true, false. And we also have the bad, good axis here. All right, number 4. And if you're doing this, if you're watching this as a video, if I ever get my ass to do it, you can pause and like answer yourself, right? And you don't have to do it Dora the Explorer style either. Number 4 looks very similar. And this one trivially looks true because all we did was add a y here, and we know that the y is in here, so we'll say incrementally that it is true or good. The next question is lambda xy as the parameters and xy zxy. Why are they doing the same thing? Did I? Oh, what they did was, so they've dropped the z, and we know we have a z in here. So that one is bad. It's evil, in fact. It's a trick. All right. So we've done that. All right. Next exercises is it normal, beta normal form, or does it diverge? First one, lambda x, and then followed by 3 x's. This one is beta normal form because there's no arguments here. We can't reduce it any further. We can't do anything to it. So this one is normal. Wow, this feels really bad to write, like, especially for someone who's so abnormal. I don't like the idea that there's something normal or not normal, right? Okay, so that was number 1. Number 2 is lambda zz, z dot zz. So it's basically doubling whatever it gets. And then we pass in y dot y. So this one sounds like it's not going to be normal, right? Just because, yeah. So here we go. We're going to replace, this is the argument, and this is the function that we're going to apply this function to this argument. So, oops, I'm so used to writing x. Plug for Bic erasers, Bic Mini. so the head here is z, so we're going to put the argument into this function as z. We're going to assign z to this function. And so now we go into the body, which is zz, and each z, we're going to replace it with this. So we end up with lambda y dot yy for the first z. So you can see this z turns into this, right? And now we're going to do the second z. That turns into the same thing because of this rule. So we end up, we started with this, and we ended up with this. Is it closer? No, because we're just going to end up with, if we do this again, we're just going to end up with the same thing. The fact that these are different letters, it doesn't matter. There's something called alpha equivalence. This y only makes sense in the scope of this function. So these z's and y's, they're not the same or different in that sense, or they're different. All right, so the answer for number 2 is it diverges. Does this all make sense so far? All right, we're going to go to the next question now. Number 3. This is on page 43, by the way, of the book, if you have it. I'll tell you if it's a good book after I'm done with it, but everyone tells me it's good. So here we go. We have a function, and we're going to apply the argument z to it. So our head in this function is just x. So we're going to say x gets assigned z. Oops. And now whenever we see x here, we're going to replace it with z. So we get back z, z, z. We drop the head of this function because we're actually evaluating it. We're removing it. So hopefully that makes sense. And this is a normal form. We can't go any further than this, so we can say normal for number 3. All right, so the next exercise, we're done with this part. Now we're going to do some beta reductions. This is probably what is harder, and this is where I'm going to make mistakes, if I haven't already. Should we look at the answers real quick to see if we made any mistakes? Let's see. So for the previous page, it said, sorry, I moved you. Thanks, Cryptic. I'm gonna, Charlie, thanks. I'm gonna get rid of these nails because I can't do shit with them, like buttoning my shirts, putting my earrings on. Typing I've gotten used to, but I make more like mistakes, more typos. So it's a little annoying. The hardest thing is just like I can't do things as well with it. But I'm doing all right. I literally have to be out of my apartment, like move everything out today, and instead I'm streaming. So, yeah, I don't know if that's copium or what, but not the best choice. I'm not moving. I've been at my girlfriend's place forever. It's just that I had this studio that I've been paying for no reason. And get this, the lady that owned it, she died. So then in France, the inheritance is actually very expensive. It's like, whatever, 50% taxes or something like that. So most times when the children get their inheritance, they generally just want to sell it so that they don't just, pay. They get something out of it. So anyway, the 15th is the last day of the lease. So I have to be moved out by then. However, I'm leaving to Germany on Wednesday, I think. No, Thursday. So I kind of have to really move everything out um in the next day or two. So yeah, it's a pain. But I'm sort of just trying not to think about it too much. My stuff is just going to storage. Like everything that I need to live with is already here. So, you know. But thanks for checking in. Hope to see you soon and hope you're feeling better. All right, so let's see. This one is a combinator. This one isn't. We're right. Yes. We didn't say here, but oh, 3. Yes. So we got that right. 4 is yes, and 5 is not. We got that right too. Oh boy. All right, so next one here. Does it diverge? It says the first one doesn't diverge, so normal. This one does diverge. Did we say diverge? Yep. And this one doesn't diverge. All right, perfect. We got those all right. So we can go back to our beta reduction now. Take it easy, Charlie. Hope you get some good sleep. ABC can't be arsed. ZZ. WV. W. All right, that's the thing. I didn't copy. I did one of these wrong last time because I didn't copy it right, so I'm just double checking. All right, so we have this one expression, we have this argument here, and we have this other argument. This argument, this argument, and this argument. This argument is a function. So we're going to ABC, whenever you have multiple parameters in the head, you can basically reduce it like x, y. X, y is the same thing as saying it's a function x where it takes in another function y, x, y. So each of them just have one parameter, you see. Um, that's the way you think about this as currying. Here. So you can imagine if you passed in a 1 here, x would be 1, but it would return you a function. And then the function, you pass in a 2 to this function that goes into y, and then it returns you 1, 2. So when you pass the first argument, you actually don't get back the full answer, you just get back a function. That function, however, knows that x is 1. It bound x to 1. All right, so we're going to turn this ABC into I don't know if I would call it simplified format, but like the obviously curried, explicitly curried format. So we got to match our parens, right? So now this one matches. So we have 1, 2, 3, 1, 2, 3. Wait, how did I do the wrong thing? This one matches this. I think I put one too many. All right, so now we have two Z's, and then we have this one will do the same thing. Just fits. Do you see it all? Yeah. So I've split up the Y and the V into the explicitly curried format. All right, so this Z is the first argument, and it's going to go into, we go left to right. This is our first lambda expression here. You can see it's a full lambda expression. This one matches with this, so it's a whole function. And so this Z can be applied, well, we can apply this function to Z. So we'll take the A and we'll turn it to Z. And so what do we end up with? We end up with, we get rid of this part, we have B dot C dot C B, and now we see an A, so we replace the A with a Z. And there we go, we've done this part. So we got rid of this parentheses here, so now we have only two parentheses, you see? We got rid of this Z here because we used that for the as an argument, so we have one Z left, one Z. And then this function still, we've done nothing with it yet. So we just carry it over. Right? So now we can do the same thing with the Z here. We can apply it to B. So we do B is equal to Z. And so we rewrite this. We're using this so we get rid of that. Now we have C dot C, and now B is Z, so it's C, Z, Z. We got rid of this Z because we used it, and now we have lambda W dot lambda V dot W. We're running out of space. So now this is an argument that can go in as C, so we do C is equal to, oh God, I hope you can see this. C is equal to the W dot V dot W. So now we're going to replace that. So we get rid of this. So now we just put this C becomes that. So we do W dot lambda V dot W ZZ. Right? So now we can apply the Z as the W. So you can do this in your head. Let's do it in our head, right? So we're basically saying W is equal to Z, right? Assign Z here. So now in this body, we're just going to replace any W's with Z. So this turns into lambda V dot Z, Z, because we got rid of this Z by, we applied the function to it. So now we have this lambda vz, and we can apply z as v. However, z here is a free variable, so it's this function's going to always return z no matter what is given to it. So this guy doesn't really matter much. So the answer is going to be z. Let's see if that's the right answer. Yep. I won't check how they did the work, but that's the right answer. Yay. Easy. Are you doing this yourself too, Ice, or not? You're like, I already know this so well. I don't need to do this. Yeah, exactly. The people who watch these know this shit so much better than me. All right, problem number 2. Problem number 2 is x lambda x dot lambda y dot x y y lambda a dot a b. All right, you can work on that for a second if you're watching this in the video later. I'm gonna get water because I'm thirsty. That's why we drink. I got a Stranger Things cup from Burger King. Sometimes I get their veggie whopper. I haven't watched Stranger Things, but this guy's like a monster looking thing in the cup. I don't know what that's about. Where did I put this? All right, so let's continue now. Here's the problem, right? Well, this looks like a curried function, so I'm just going to put parentheses here just to make it easier for me to at least understand. So we go left to right here, and we can see that this is one whole function here that ends. And this would be the first argument, and here would be the second argument. So we're going to apply this function, the x function, to this argument, which is the identity function. So we basically say x is equal to this identity function here. So wherever we see x, we're going to substitute it with that. So we do lambda y dot, and now we have this x, so it turns into lambda a y y. There we go. All right. We got rid of this parentheses, the outermost one, because we actually evaluated this, we applied this function to this, which we're going to drop also. So we drop this because we used it, and now we have b left. And so we're going to now apply this function to b. So we'll say y is equal to b. And we end up with the identity function. We're just looking for y's here now, 2 y's. So then we end up with bb, because this y turns into a b, this y turns into a b, and we drop that. And so now we have the identity function and 2 parameters. So we're going to apply b to this identity function, or no, the other way, the identity function to this b. So we say a is equal to b. And so we end up with b here, and this b still carries over, and the answer is bb. This is page 43. What's the answer on? Yep, that's the right answer. The answer is on page 46. All right, so now we're doing question number 3. Do we have enough space? I guess like if we use about half, maybe it's enough. Is it maths? No, I guess a little bit. It's lambda calculus. It's from a book called Haskell Programming by First Principles. So we're learning how to program in Haskell, but we first have to start by understanding lambda calculus because it's kind of a foundation of, using Haskell. So I guess it's a little bit like math. All right, so question number 3 is y. That's the identity function. And here is xx, so it's basically going to double whatever you give it. And here is zq. So it's going to just tack on q to whatever you give it, right? So these are 3 functions. The identity function is going to return whatever you pass it. We're going to basically apply the identity function to this. So we already know, just like trivially, that we're going to get this back, right? So just without thinking too much, we can just say we'll end up with the same thing. So we just drop the identity function, x, and then we have this function, zq. So this function is going to double whatever you give it, right? So we can just apply this function to this argument, and we know we're going to get 2 of these. So let's just double it. You're not a coding guy? I don't know. What's code, what's not, especially these days with AI? Like, anyone can be coding, right? Okay, so this function is basically going to take in what you give it and apply a Q to it, right? So I wonder, doesn't this mean I can just take this and add a Q to it? Nice. I need to do more math. So my assumption is that it'll just take this and apply a Q, but let's go through it. We're going to replace Z with this argument, which is basically itself. And so we're going to see Z here. We're going to replace it with this. And then we add the Q. So yeah, it basically, all it did was add a Q to whatever you pass in. And now we have a pretty simple function where it's going to add a Q to it, right? So we can give, we know that it's just going to add a Q, so here's the input, here's the output. So the answer is, when we do beta normal form for this, or beta reduce this thing, we get back QQ. Let's check that. That should be page 46 or so. Yep, it's QQ. Hopefully this is making sense to you guys that have been following. Let's do the next. Thanks. Let's do the next problem. Once we get to the part of the book we're actually programming, we won't be writing on paper anymore. This is question number 4. Z dot Z identity function. Z dot Z Z. Oops. Z dot Z Y. It says hint alpha equivalence. I'm not sure what that hint's going to really help us with here, but let's maybe we don't need the hint. All right, so this is just the identity function like we said. So we're going to be applying this function to this argument. So we just get this back. So we can just basically drop this. And this one is going to double whatever we give it. So let's just double this. Z dot ZY. Z dot ZY. And so this one is just going to add a y to whatever you pass it, right? So here we'll just spell it out. Z is going to equal this argument. So now we go and look at the body and we're going to replace it. So we do Z dot ZY. We've replaced the Z with this, right? And then we have the Y after it. So here we go. And then we're going to apply this function, which tacks a y to whatever you give it to y. So we should end up with y. Let's see. Yep, that was the answer. I don't really know why they told us about alpha equivalence. Doesn't feel like it was a big deal. All right, next problem. There's 7 of these, so we're almost done. Yeah, it was the right answer. The right answer is y. Why did you think I did it wrong? Are you doubting me? No, I doubt myself already for enough for all of us. All right, we have x, y, x, y, y, x, y, x, y, y, x, y. I don't know what I'm doing. Okay. And then we have our identity function again. And another y. So since this is basically a curried function, I'm just going to do this to make it easier for me to think about. Makes it really explicit that there's a function that takes in one parameter that returns a function that takes in one parameter. Um, all right, so the first thing we do here is we always go left to right. So we're going to apply this function to this argument. So we're going to say x is assigned this identity function. So whenever we see x in this body, we're going to replace it with this. So here we go. And here's our first x. So we're going to do yy here. And then followed by two y's. Right? We got rid of one parentheses at the end here because we beta reduced once. So this outer one is gone. And we applied the function to this argument, so that's gone, and now we just have y. So there's a whole bunch of y's here. Okay, so we still have this function here. So we're going to give it a y, right? So we're going to say y is assigned y, which means nothing changes. So which means we can basically just copy this. Right? All right, so now here we have the identity function and we have two arguments y. So we're going to give y, we're going to apply the identity function to this argument, which means it's just going to return us the same thing back. And then we copy the second argument over and we end up with yy. Let's see if that's correct. This is question number 5. It is yy. It is indeed yy. So now we're going to do the penultimate question. I chipped this nail moving. How terrible. So this year, I want to do more conference talks. I applied to ElixirConf, which is in ElixirConf EU, which is in Malaga, Spain this year. I submitted 3 different talk ideas. Maybe one of them will be accepted. I already did 2 talks recently in Elixir themed conferences, so maybe they're sick of me. We'll see. I also proposed a talk for VCFE Berlin. It's like Vintage Computing Festival East or Europe. No, it's probably Europe. and that's in Berlin. And I suggested talking about 6502 assembly language programming. So that would be really fun. I think I might be late submitting that talk, so we'll see if that happens. No, no problem, Ice. You're just checking that I got it right. Okay, we're doing the next one, number 6. Yeah, I don't know why it mentioned alpha equivalence. I think if you maybe try to do it with substitution rules, that like you might just get confused. So maybe it's easier to switch like all the second Z's to like a different letter. I don't know. Anyway, let's do this next one here. We have a function that doubles. This is a combinator, right? Because all the elements in its body is in its head. Now we have another function here. This is not a combinator because it has a free variable a. It's not in its head. And then we have c, its third argument. All right, so we're going to go left to right. The first thing we know is we're going to double this argument. We're going to take this function and apply it to this argument. We know this function basically just doubles whatever it gets in. So we're just going to do that without explicitly writing the substitution rule. Does that make sense? We just double this. And then what does this function do? It takes in something, it just adds an a to it. So we're going to take this function and apply it to this argument, which happens to be itself, but don't tell it that. Which means I can pretty much just rewrite it and add an a to it at the end, right? And then add the c from here. And now what do we have? We have the function that adds an a to it, so we know whatever we give it is going to get an a at the end. We're going to apply it to this argument a, so we know that turns into AA, and should we have AAC. Let's see if that is correct. Yep, we're right. Let's go and check out the last problem now. Let's see. Lambda calculus is variable substitution as an algebra and function application, a very core set of mathematics not covering arithmetic or numbers. Alpha equivalent sounds like what you name variable doesn't matter. Right, exactly. It doesn't that's what it means. But I wasn't quite sure why it said hint, so we didn't need to worry about it. Okay, thanks for the answer. Vogish Carp. Love that name. All right, so we're in our last question in chapter 1, I think. The book, by the way, is Haskell Programming by First Principles. Seems like a great book so far, but we're still in chapter 1. All right, X, Y, Z, X, Y, Z. X, Z, Y, Z. They're making it harder here. X, Z, XA. So these two here, these are both like free variables. So whatever you pass in, it's just going to return Z and A. So that'll probably be easy. And here, this is a combinator because all the variables in the body are in its head. So let's just rewrite this in a explicit curried format. We just match up the parentheses here. 1, 2, 3, 4. 1, 2, 3, 4. And then we have these two functions that we just copy. Hopefully you can see that. Um, do you already program Haskell Vogeshkar? All right, so we have this one big long function. We have two parameters, right? So for the first thing we're going to do is apply this big function to this first parameter. So we're basically saying x is going to be, we're going to be substituting x for this function x dot z, right? So where we see x in this body, we're going to replace it with, we're going to substitute it with this function. So let's do that. This doesn't substitute, it's the same thing, y. Now we keep going, we haven't seen any x's yet. Here's our x. So we're going to replace it with this. Now we have a z, a y, a z, and then 1, 2, 3, 4, but we reduce it by 1 because we did, we just got rid of this outermost one. 1, 2, 3, 2, 3, 1, 2, 3. So it matches. We applied it to this term here, so we don't need to, we can drop this, and now we have XA. Can't wait to get further and actually program in Haskell. I tried, doing the learn you Haskell for great good, and I was programming Haskell, but I didn't really feel like I learned it. So I heard this is a good way. Anyway, so we're going to take this function that takes y as a parameter, and we're going to substitute y with this. So here we go. Y is equal to x dot a. Now we're going to go and replace y in here with that. Here, no, that's not a y yet. Here we go. We have a y here, so that turns into and then we should close it with 2, right? So this matches, that matches, this matches, and that matches. Graham Hattori's Programming in Haskell. Is it a good book? All right, so now we have this. You can see it's one big expression, so we have we have no arguments to apply it. So we're going to now look inside of it left to right and see if we can simplify it. So here we find our first thing we can do, which is like we have this function with an argument. So we're going to apply it. You see that whatever we pass in here is just going to it's just going to return z no matter what. which is kind of funny because we're passing in a z anyway. But if this was a b or whatever, it still would be returning a z. So this turns into a z. Let's just rewrite this. So this whole thing turns into z. And then we can copy the rest of this. Right? All right, so that looks good to me. I'll have to check that book out. Well, since I started with this, I hope I can just continue. So we have another function here that we can apply that's always going to return a. So we know that it's going to basically be this thing here is going to turn into an a. So we end up with this. And now it looks like there's nothing more I can do. It looks like the answer is z dot. It's this. But let's see. Somehow it doesn't feel right, so maybe I did something wrong. What? What the heck? So the only thing that's weird is that they called it Z1 here. So these Z's must not be must be different Z's. Where did that happen? Okay. So they simplified it to basically what we got. But in this step, this turned to Z1. And this turned to Z1. And this turned to Z1. So let's see here. Because this Z here is not the same. This Z here is not the same as this Z. Right. So because we're basically saying that whatever we get, we return a Z, but we already have Z's in the body, we need to give it a new name. Yeah, this is a free variable Z here. So like one thing we could have done is just like change this to some other letter, and that would have made it a lot easier. Just because this guy here causes problems. This guy doesn't cause problems because this free variable a, it doesn't exist anywhere else. But this z is not necessarily the same as this z when we evaluate. All right. Well, we kind of got the right answer, but we needed to rename the variable, which means we're done with chapter 1 in this book. What's next? What's coming up? I'm trying to figure out how I can stream me learning Haskell. Yeah, gotcha. I mean, it makes sense. Um, what's gonna happen? We're gonna end up using the REPL. Um, are we gonna program? Looks like it. So I'll figure out something here. Hopefully they have exercises. Let's see. Yeah, they have exercises, so we can definitely do those. And we'll do that next time. So I'm going to read a little bit of the book next time, and then once I get to the exercises, we'll stream again. I'll probably like split this up and post them on YouTube or whatever. I don't know. We'll see. But thanks for hanging out with me, and I will talk to you guys later. I'm gonna go finish my move now, or hopefully finish my move out of my studio.